Okay, so welcome back. We are going to have now our third and fourth problem for the shear stress. So for the third problem, we have here a connection. Okay, so these two members are connected by a bolt. So this setup could be found in some parts of mechanical parts like motorcycle on the concept of a machine that is connected by this one bolt and members. So we are going to find the smallest diameter of bolt that can be used in the clevis shown in the figure, wherein the P is set to be 400 kilonewton and the shearing strength of the bolt is 300 megapascal. So the first thing to do is, I think we should have the FBD. Say this is the bolt. So if this is the bolt, when we apply the force, it will be cut into two. Why two? Because this section is restrained so that two sections are being cut. So this is what we call the double shear. So this concept was discussed on the earlier video sessions, wherein we will just have to multiply our area by 2 because we have two sections that are being cut. So this cut section, if we will take a look at the cut section, that is actually the cross section itself of the bolt. So simply we substitute the 400 shearing force here. It is being multiplied by 1000 because this force is in terms of kilonewton, and then we will be consistent that to express this force into Newton. That is why we have multiplied 1000 there, because to recall, in 1000 Newton there is 1 kilo Newton. So 1000 here is a conversion factor to express our shear force in terms of Newton. Okay, so others, tau is already given in megapascals. Again, this is shear area. Okay, we multiply 2 times the area of a single circular cross section, pi d squared, and then manipulating the equation again, we come up with d. Okay, we come up with the diameter. Okay, so that is for the problem number 3. Okay, so next, number 4. So for number 4, we have a pulley setup wherein the pulley is attached to this shaft. So the connection, because this pulley can be detached into the shaft and can be connected again and locked by the key. So this is what we call the key. This is the key here. This is the key. Okay, so the key is inserted to a slot here. So maybe have that figure here. Perhaps we can enlarge this one. Okay, okay, so this is the slot I'm talking about. That space is intended to connect the shaft and the pulley. Okay, so what will be the tendency in the stress of that key? So basically, since that is the locking member, between the shaft and the pulley, it will be subjected to a cutting force. So basically, it will be cut this line. May I highlight that line? So this line, because if this is being rotated, then there will be a force in the shaft, and the force in the shaft would tend to cut this member along this line. Okay, say this is the line. Okay, it will cut along that line. So F is the force. Again, may we draw that force. So this is the force F in the key, wherein the internal effect is to be resisted by this capital letter V. This one. Those forces are represented by a single force V. And if we are going to take summation forces along the axis of that, you just say that V is equal to F. Now, how can we now derive our F? So in this figure, this is actually the figure of the FBD. Okay, so this is the FBD. So relating our torque, so torque is within the shaft. It is actually occurring or located, or it is a couple that is applied in the axis of the shaft. So say if this is the axis of the shaft, torque is applied to the axis of the shaft. So meaning, if the parallel axis on the body, if we have applied a couple there, the result is a torque or twisting or torsion. Okay, twisting, or this is twisting force or torsional force. So on that torsional force, of course, we wanted to refer that to the point of origin of the axis of this one. Okay, so in order to have a relationship between F and this torsional force equivalent to that 2.2 kilonewton meter, we will just have to take moments at the point of origin of the torsion. Okay, so basically this is the summation moments at point O is equal to 0. Okay, so see, this is point O, or the point of origin of the axis of the body or the shaft. So doing that, we have what? Counterclockwise torsion, that is denoted by negative T, isn't it? And then F is a resisting force. By the way, F here is placed against the direction of this. Okay, so on the free body diagram, F again is placed against the direction of the rotation. That is why that is going towards right, because this is counterclockwise. So going back to summation moments, we have negative T counterclockwise plus what? F. F is a force. We are actually performing a moment, so we must have to multiply this by a certain distance. So our reference point is point O. So therefore, what is the distance of F to point O? So again, that is given in the problem. That is 0.03 meter. Where did we get this value? So 0.03 meter is half of the diameter of the pulley, and that is 0.06 meter or 60 millimeter. So 60 millimeters just divided by 1000 to make it in meters. So 60 divided by 1000 is 0.06. So we have that one because we are referring to the radius only to locate F up to 0.0. So that is why F times 0.03. So there is no any other force. Then we can close it and equate it to 0. That is why from this we have this one. T is equal to 0.03 F. Now substituting the values, 2.2 kilonewton meter. So note here that the distance is in terms of meters. So for the meantime, do not bother yourself on kilonewton, because on the equation, the distances must be consistent first, because it is present on both left and right of the equation. So 2.2 here is in terms of kilonewton meter, and then again 0.03 is meter. So basically, if we perform this, we will come up with the force unit 73.33 kilonewton. You may opt also to already convert kilonewton meter in terms of newton. So anyway, what is important here is that on the left and right, you must have to be consistent with the units. So do not ever express a left side equation wherein a left side equation contains millimeter and then for the right side contains meter. So that is actually the common error in manipulating this type of equation. So the tip here is always that be consistent with the left and right side of the equation. Okay, so after getting our F is actually also the shear force, isn't it? Because of this, okay. F is external force. It is being resisted by internal force, series of shear along the cut section. So it is denoted by a single letter V. So proceeding now, we have to apply this formula. We cross multiply that, and then here we go again. V is equal to the tau times A. Okay, so where V is equal to F, 73.33 kilonewtons, and then the area. What is the shear area? The cut area. And what is the cut area? B times 70. 70 here is the length. B here is the width, denoted by B. Okay, that is why 70 times B. So note here that in the area, we have already expressed the area in terms of millimeter units. So therefore, bear in mind that if we have millimeter, we should have a Newton unit for the force. So applying now this formula, this one, okay, 73.33 is kilonewton. Again, we have a conversion factor to make it in Newton. This is equivalent to tau. Tau here is given 60 megapascals, and then this is the area, 70 times B, and this is it. We have obtained the value of the width of the key. Okay, so this is problem number 3 and 4. So please stand by for the next video in order for us to finish problems in shear stress and bearing stress as well. So thank you. Have a more practice. So do not stick only to these problems. On You may explore problems available in books and other references. So thank you.